All right, we are about to get to the very heart of the matter, and I mean that literally. In this explainer, we're going to break down the fundamental building blocks that make up, well, everything. You, me, the chair you're sitting on, everything.
So let me just ask you a question. What are you really made of? I mean, if you could zoom in past your skin, past your cells, all the way down, what would you find? Well, the answer is this incredible, tiny universe of particles. And to understand it, we're going to need a roadmap. Here's our game plan. We'll start by exploring the atom's tiny core. Then we'll figure out how each element gets its own unique ID. After that, we'll get into ions and isotopes, learn how to actually calculate an atom's weight, and then wrap it all up by figuring out where those electrons are supposed to go.
Okay, let's dive into our first section, the atom's tiny core. We are zooming right into the heart of all matter. And this is the atom. Think of it this way. It's the smallest possible piece of gold that is still gold, or the tiniest bit of oxygen that is still oxygen. It's that fundamental point where, if you break it down any further, it just stops being what it is. So, what's inside one of these things? Well, right at the center, you have this super dense core called the nucleus, and that's packed with protons and neutrons. Then, whizzing all around that nucleus, you've got this cloud of tiny, super energetic electrons.
Now, each of these particles has its own electrical charge. Protons are positive, electrons are negative, and neutrons, they're neutral. They don't care either way. This whole setup creates this powerful opposites attract situation. The positive nucleus has this incredible grip on the negative electrons, holding the whole atom together.
And here is where things get just mind-bending. To give you a sense of scale, if an atom were the size of a giant sports stadium, the nucleus, the part with almost all the mass, would be a tiny marble sitting right in the middle. The rest of it? It's pretty much empty space.
And those electrons flying around? They're basically weightless in comparison. You'd need almost 2,000 of them just to equal the mass of one single proton. But don't let their tiny size fool you. Their negative charge is the engine that drives pretty much all of chemistry.
All right, on to section 2. So how does an atom of gold know it's gold and not, say, lead? Well, it all comes down to one singular, super important number. And this is it, the atomic number. We call it Z. It is simply the count of how many protons are in the nucleus. That's it. This number is like an element's unchangeable fingerprint. It's the one and only thing that defines what element an atom is. I mean, it's that simple. You've got an atom with 6 protons, bam, it's carbon. Every single time, no exceptions. Got one with 8? It's always oxygen. If you change the number of protons, you're not just tweaking the atom, you're changing the element entirely. Okay, section 3, ions and isotopes. So, we know the proton number is non-negotiable, but atoms can still have some variety in their charge or their weight. And that brings us to 2 really crucial concepts, ions and isotopes.
First up, let's talk ions. An ion is just a word for an atom that isn't neutral anymore. It's got an overall electrical charge because it's either gained or lost some electrons. If it loses an electron, it has more protons than electrons, so it becomes a positive ion, or a cation. If it gains an extra electron, it becomes a negative ion, an anion. Simple as that.
Now, an isotope is a different beast altogether. This is all about weight, not charge. Isotopes are atoms of the very same element. So they have the exact same number of protons, but they have a different number of neutrons crammed into that nucleus.
Carbon is the perfect example here. Just look at the table. Every single one of these has 6 protons, right? That's what makes it carbon. That's its ID card. But check out the neutrons. Carbon-12 has 6 neutrons, but the heavier carbon-14 has 8 of them. They're all still carbon, just different versions with different weights.
Okay, section 4. So if elements have all these different isotopes with different weights floating around, how in the world does the periodic table list just one single number for atomic weight? Well, it's all about finding a special kind of average.
That number you see on the periodic table is called the relative atomic mass. Now, this is key. It is not the weight of any single atom. Instead, it's a weighted average. It takes into account how common each of those different isotopes is out in nature.
So to do this calculation, you really only need 2 bits of info for each isotope. Its very precise mass and its natural abundance. Abundance is just a fancy way of asking, what percentage of all this element in the world is this particular isotope? You can see here for hydrogen, for instance, one isotope makes up more than 99.9% of all hydrogen out there, while the other one is super rare. And here's the formula that does all the magic. Now, don't let it scare you. It looks way more complicated than it is. You just take the mass of the first isotope, multiply it by how common it is, and then you do the same for the second isotope. Add those 2 results together, and that's it. That gives you that one useful average weight you see on the periodic table.
And for our final piece of the puzzle, let's head back to those electrons. See, they don't just fly around randomly. Their organization follows some very strict rules, and these rules are basically the foundation of chemistry itself. Electrons occupy these specific energy levels called shells. You can picture them kind of like the layers of an onion. These shells get numbered, starting with n equals 1 being the closest one to the nucleus. And here is the golden rule. Electrons are lazy. They always fill up the innermost shells first before they even think about moving to the outer ones.
So how many electrons can each shell actually hold? It all comes down to this one beautifully simple rule. 2n squared, where n is just the shell number.
Let's test it out real quick. For the second shell, n is 2, right? So the formula is 2 times 2 squared. Well, 2 squared is 4, and 2 times 4 is 8. So the second shell can hold a maximum of 8 electrons. This simple little piece of math dictates how all the elements bond and react with each other. It's that important.
So we've done it. We've built the atom, from its charged nucleus to its perfectly ordered electron shells. We know how it gets its identity, its weight, and where its chemical power comes from. The real question this leaves us with is, how does this one tiny invisible structure end up dictating absolutely everything? I mean, from the fizz in your soda to the nuclear furnace that is the sun, it all begins right here. That's the power of the atom.